Dear colleagues, today is July 24th. First speaker is Professor Hwanju Dong. Title of talk, on a conductivity problem with imperfect bonding interfaces. Please.
Okay, so first I would like to thank the organizers for the very nice invitation. It's my great pleasure to give a talk in this ISAC Congress. So this is also my first time to Central Asia. Yes, I enjoy everything here. Okay, so today I'm going to talk about some recent work jointly with Jordan Yang. He is now a postdoc at Brown University, and also my former student, Han-Ye Zhu. He's now a postdoc at Duke University. So we studied the conductivity problem in composite material. So we consider so-called imperfect bonding interfaces, which I'm going to explain a little bit later. So in this case, we have this potential function, which is discontinuous across the interfacial boundaries. So this model is important because it has applications in a biological system where there's a membrane structure. Okay, so my talk will focus on so-called composite material. So composite material, an example is the fiber reinforced material. Examples like fiberglass, plywood, polymer composites, and also even concrete, which we use in everyday life. So these materials are made by combining two or more natural or synthetic components together, so that as a whole they are stronger than individual materials. So composite materials were actually used a long time ago. So more than 6,000 years ago, people found that if you combine straw and mud together to create bricks, they are stronger than the bricks just made by mud itself. So today, composites are used extensively in different areas, for example, aviation and also aerospace. So we want to study this problem by using PDEs. So in composite materials, so we have inclusions represents different materials. So they are often very closely spaced, and they may even touch with each other. So in this case, they can generate cusps, and because the coefficients and the data in the different materials, they are different, so we have a jump discontinuity and also jump data. So because of this, we can not use the classical PDE theory to study this problem. And here's two cartoon pictures of this problem. So the picture on the left is the 2D picture. You can consider this as a cross-section of 3D composite material. So we have this domain, and then we have subdomains. And you can see that here D1 and D3, they are very, very close to each other. And D3 has a subdomain, which is D2, and D2 is also very close to D3. Okay. And in this place where they touch each other, you can see there are cusps. And the picture on the right is the 3D picture. So we have these blue fibers, so they are called fibers. And then we also have this yellow, which is called the surrounding matrix. Okay. All right. So in this problem, there's a phenomenon which is called the field concentration phenomenon. And when two inclusions in a composite in a material, they are very close to each other. And also their material property, they are different from each other from the surrounding matrix significantly. Then this may lead to build up of stress or field concentration in this narrow region. So this is called field concentration. So understanding the field concentration phenomenon quantitatively is important because this field concentration may cause material failure. On the other hand, in some situations, people want to create this field concentration. For example, in medical area. This theoretical analysis related to the field concentration go back to a long time ago. So, for example, Keller in 1963, and also Flaherty and Keller in 1973, where they studied the so-called effective medium theory. So this is related to the this field concentration phenomenon. Okay, so let me set up this problem by using a PDE language. Let's assume that omega is a bounded domain in RD. D is the dimension of the space. And this omega contains, say, m disjoint subdomains, D1 up to Dm. And these are sometimes called fibers, sometimes called inclusions. So the problem can be modeled by this elliptic system. Okay, so this is second order elliptic system. D alpha, A alpha beta, D beta U is equal to this right hand side, which can be expressed in terms of divergence G plus F. And here, A alpha beta are piecewise defined functions and satisfies certain ellipticity condition. So an example for such system is the Lamé system, which is a famous system in the elasticity theory. So for the elasticity problem, this U is a vector. So this stands for the displacement. And then in this case, the dimension of the U is the same as the dimension of the space, right? Because it is the displacement. And then the U is the stress. So in this case, it's a matrix. And for the conductivity problem, U is the voltage potential. And then the U represents the electric field. Okay. So this is an elliptic system. And sometimes we can simplify this. In the isotropic case, then the equation can be written in this form. So divergence of AX du is equal to 0. So in this case, U is a scalar function, and A can be a piecewise constant function or piecewise constant matrix. So an example is A is equal to some constant K in these inclusions, Di, and it is equal to 1 in the surrounding matrix omega tilde. So here I denote omega tilde to be omega minus the union of Di, which is the surrounding matrix. Okay. So this equation is supplemented by this transmission condition, meaning that this potential function U is continuous across the interfacial boundaries, and also this flux. So nu is the normal direction. So nu dot A times gradient U. So this flux is also continuous across the interfacial boundary. Okay. So if you consider this equation and if you impose suitable Dirichlet boundary conditions, then we have the maximum principle. So U itself is bounded in this case. So we are interested in the field concentration, which is the bound on the gradient of U. So this is stress or the electric field. Okay. So there are many work for this problem. So that's the elasticity and the conductivity problem in composite material. This has been studied for more than 2 decades. So in 1999, Bubashka, Anderson, Smith, and Levin, they studied a homogeneous linear system from elasticity, and they use certain some numerical methods to find that the gradient U is actually bounded independent of the distance between subdomains. So even if we have cusps, still this gradient U is bounded in this case. And then this was proved rigorously a year later by Bonnetia and Vogelis. They actually consider some special case, so the scalar case when 2D, the dimension is equal to 2, and the inclusions are disks of comparable ready. Then they proved rigorously that the U is actually bounded in this case, independent of the distance between the inclusions. And later, Yayani and Vogelis, a bit later, they proved extend this result to more general divergence form elliptic equations with discontinuous coefficients. And they prove that this solution U is globally Lipschitz, and also it is C1 alpha up to interfacial boundary in each subdomain. Okay, so even though du can be continuous across the interfacial boundary, but if you restrict this solution in each subdomain, it is still C1 alpha. So even if you consider this cusp, so let me draw a picture. Say we have a domain with two inclusions. Okay, so what they prove is that the solution is C1 alpha in say D1 and C1 alpha in D2, and it is also C1 alpha in this narrow region. And this norm is independent of the distance between these two inclusions. Okay, so that's their result. Can we go back to the slides? Okay, so their result is for scalar equations. Then later, Ian Lee and Louis Nierenberg extended this to elliptic systems. So in particular, they can deal with Lamé system. Okay, so this is the case when this conductivity constant is away from 0 and infinity. Then if this conductivity constant is allowed to be 0 or infinity, then the situation is very different. So when this k is equal to infinity, that corresponds to the perfect conductor case. And when k is equal to 0, that corresponds to the insulated case. So first, again, this is by numerical methods by Bodziarski and Carrier in '84, and also Keller in '93, and also Malcolm Scoff in '96. They observed numerically that in this case, this gradient U can be unbounded as the inclusion gets close to each other. So the first part of my talk will be focused on this perfect insulated and insulated conductivity problems. All right, so for the perfect conductivity problem, we can rewrite this equation into this system. So U is a harmonic function in the surrounding matrix in omega tilde, and also this gradient U is equal to 0 in the union of D1, D2. So meaning that U is a constant in D1 and another constant in D2. Then, because of the continuity, this transmission condition of U, so U is also equal to this capital Ui on the interfacial boundary. So the last condition is the zero total flux condition. So if you integrate this normal derivative of U on the boundary, on the interfacial boundary, then it is equal to 0. So this is you can easily derive this equation by using variation method. Then for the insulated problem, the equation can be written also in this form. So again, U is harmonic in the surrounding matrix, and on the interfacial boundary, U satisfies this Norman boundary condition. So partial U, partial nu is equal to 0. Okay, so in both cases, formally U satisfies these two transmission conditions across the interfacial boundary. Regarding the existence and uniqueness of solutions, we can use variation argument to prove the existence and the uniqueness of weak solutions. So what we are interested in is the blow-up behavior of a gradient U in this narrow region. Okay, so for the perfect conductor problem, meaning that k is equal to infinity, there are many known results in that direction. So first by Amari and his co-authors in 2005 and 2007, they studied the 2D case when the inclusions are circular, so disks, meaning, and they obtained the optimal blow-up rate of the gradient of U, which is 1 over square root epsilon. Okay, so in fact, they consider both the case when k is equal to infinity and also k is equal to 0. And then their result is later extended by Yuan to the case when the inclusions are bounded and strictly convex smooth domains. All right. So in 2009 and 2010, Bao, Li, and Ying, they consider the high dimensional problem when k is equal to infinity, and they prove that if in the 2D case, the Bohr operator is 1 over square root epsilon, and in the 3D case, it's 1 over epsilon times log epsilon, and in 4D or higher, it's 1 over epsilon. And they also prove that these rates are optimal and independent of the shape of inclusions. And you can see that when the dimension increases, the solution becomes more and more singular, because in 2D it's 1 over square root epsilon. For example, in 4D or higher, it becomes 1 over epsilon. Okay. So how about the case when k is equal to 0? So in this insulated problem was actually less understood. So first, again, in the paper by Bao, Li, and Ying, they prove that in 2 and higher dimensions, the Bohr operator is at most 1 over square root epsilon. So that means the gradient u is less than or equal to some constant c over square root epsilon, where epsilon is the distance between subdomains. So whether such rate is optimal was open problem. And in 2016, Yun proved the following result. So he considered the 3D case, and the inclusions are both radius 1, centered at 1 plus epsilon over 2, and minus 1 minus epsilon over 2, so that the distance between these two balls is exactly equal to epsilon. And also he assumed that u minus some harmonic function hx is equal to big O 1 over x squared as x goes to infinity. Then he proved that on the line connecting two closest point between these two inclusions, so that's 0, 0, x3, where x3 is between minus epsilon over 2 and epsilon over 2. He showed that this gradient of u has this upper bound, which is epsilon to the power square root 2 minus 2 over 2. So this exponent 2 minus square root 2 over 2 is less than 1 half. And he also proved that this rate is optimal when you choose this harmonic function capital Hx to be x1. So even though this is just a bound on this line connecting two closest point, so his result indicates that this upper bound 1 over square root epsilon may not be optimal when dimension is equal to 3. Okay, so this is his result. So after a few years, Yan Li and Zhong and Yang, they obtained this improved result when dimension is greater than or equal to 3. And they proved that the Bohr rate can be bounded by epsilon to the power negative 1/2 plus a small constant beta. Okay, so this beta is an implicit constant, which can be very small. So their proof is based on Harnack inequality. So that's why they get this small beta, as well as the maximum principle, combined with the interior estimate for elliptic equations. Okay, so a few months later, Ben Weinkorf, he obtained the following result. He proved that when the dimension is greater than or equal to 4, and the inclusions are unit balls, then he can make this beta to be less than beta n, where beta n goes to 1/2 as n goes to infinity. So his proof is quite different from the proof by Li and Yang. He actually used the Bernstein method by constructing sub and super solutions. But interestingly, his proof does not work when dimension is equal to 3, which is the most physically relevant case. Okay. So this optimal Bohr problem in dimension greater than or equal to 3 was a challenging problem. So this was actually mentioned in Yongbei Kang's talk, ICM talk in 2022. He said that it is likely that in 3-dimensional insulating case, so k is equal to 0, the behavior of the gradient depends heavily on the geometry of the inclusion. So let's record that in the case when k is equal to infinity, the blow-up of the behavior of a gradient does not depend on the shape. But he conjecture that when k is equal to 0, it depends on the geometry of the inclusion. It is not clear at all what is the best possible exponent in this case, and it is not even clear if such a number exists. It may depend on the position of the estimate. Clarify this is now an outstanding open problem to be solved. And so a few years ago, with Yan Li and Jordan Yang, we solved this problem mentioned in his talk. So let me set up this problem as follows. So let me denote this gamma plus to be the upper boundary. So this is xn is equal to epsilon over 2 plus some function f, depending on x prime. And gamma minus is the lower boundary of the domain. And we assume that f and g are C2 gamma functions such that at 0 they are equal to 0, and also gradient is also equal to 0. Okay? So we impose this relative convexity condition, meaning that fx prime minus gx prime is greater than or equal to some constant c, positive constant c times x prime squared. So this is called the relative convexity condition. This is actually essential. So later we prove that without this condition, the result is totally different. Okay. Okay. So let me denote this omega r to be this narrow region. Sometimes this is also called a neck region. So this is x prime is less than r, and xn is between these two interfacial boundaries. Okay. All right. So in our first paper, we consider this asymptotically radial symmetric case, meaning that fx prime minus gx prime is equal to some constant a times x prime square plus higher order term. So capital O x prime to the power 2 plus gamma. And then this is our result. So suppose that we have a weak solution u in H1. Then we can find some constant depending on these parameters, n, r0, and gamma. So n is actually the dimension of the space. Sometimes I use d, sometimes I use n. And also it depends on this C2 gamma norm of f and g. So that we have this pointwise gradient upper bound. So gradient u is bounded by some constant c, n times sup norm of u times this epsilon plus x prime square to the power alpha minus 1 over 2. So this indicates the blow-up rate is alpha minus 1 over 2. Okay. So here alpha is actually quite explicit, has a quite explicit expression. So alpha depends on the dimension. It is equal to this expression on the right-hand side. So this is a number between 0 and 1. And you can easily prove that this alpha n is increasing with respect to the dimension n. And also, as n goes to infinity, it has this asymptotic behavior. So this is 1 minus 2 over n plus capital O 1 over n squared. In the case when dimension is equal to 3, we get exactly the exponent square root of 2 minus 2 over 2 obtained by Yuan in his 2016 paper. And when dimension is greater than or equal to 4, our exponent is strictly greater than the one obtained by Weyernkopf. So in fact, we show that this this rate is optimal. We find a configuration such that in this case, this lower bound has the same exponent. Okay. So we just take this domain to be both radius 5, and the inclusions are uniballs centered at these 2 points, 0 prime 1 plus epsilon over 2, and 0 prime minus 1 minus epsilon over 2, so that the distance is equal to epsilon. And then we take the boundary condition phi to be x1. Okay. And then we show that this gradient u, the L infinity norm, is bounded below by some constant times epsilon to the power alpha minus 1 over 2. So this result, this example shows that this exponent in the previous theorem is optimal. Okay, so let me mention some elements of the proof. So for simplicity, let me assume that f and g are quadratic. So they are x prime square over 2. And then let's record that in the case when k is equal to infinity, U satisfies this normal boundary condition. Then this normal boundary condition, together with the maximum principle, we can show that the derivative of U in the xn direction is actually bounded. Okay, so our goal is to pass this information to the horizontal derivative. So for this, we make a change of variables. So we define the y prime to be x prime, and the yn to be the expression on the right hand side. So the idea is by using this transformation, we can flatten both the upper boundary and the lower boundary. Okay, so that this narrow region becomes a cylinder of height epsilon. So we denote this to be Q R0 and epsilon. And now in this new coordinate system, so let me denote this solution to be V. So V now satisfies more complicated, more general elliptic equation in divergence form with the conormal boundary condition. So even so we flatten boundary, but then the equation becomes more complicated. Okay, so oh yes, sure. Can you see this? It's not very clear, right? Maybe I should use a different. Okay, so we have this narrow region. Okay. And the distance is equal to epsilon. So this is the distance. And now we make this change of variable so that the upper boundary and the lower boundary becomes flat. And also the distance is again equal to epsilon. So this is our change of variable. Can we go back to the slides? Okay, so this V actually satisfies divergence form elliptic equation with the conormal, so-called conormal boundary condition. And our idea is use this dimension reduction argument. So we define this V bar to be average of V in the yn direction. So the idea is because we know that this U has a bounded derivative in the xn direction. So that means the variation of U in this xn direction is can be controlled. So that means if you can study the singular behavior of asymptotic behavior of V bar, then that capture the leading term of V. Okay. So if you take this average, then you can actually get this elliptic equation in a lower dimensional space. So in Rn minus 1. So this equation can be written as a divergence epsilon plus y prime square times the gradient V is equal to this right hand side. And this capital F is the average of AIN times partial NV. And you can bound this capital F by some constant times y prime times epsilon plus y prime square. So this is very small. In some sense, it's a small function. So this is good, but the problem is that if you look at this equation, it is actually degenerate. When epsilon goes to 0, the equation degenerates at the origin. So this is a degenerate equation. So the problem is then reduced to study this regularity of degenerate elliptic equation. And there are many work in the literature. For example, there's a famous work by Phipps, Koenig, and Sierpany in 1982. So they studied equation like this with epsilon equal to 0 and with general y prime to the power beta. And they obtained the George-Nash model estimate, so to speak, to this equation, but with some implicit exponent of the Holder exponent. So here we need to obtain a more precise exponent so that we can obtain optimal result. And for that, we further decompose this V bar into a smoother part and also a small part. And then for this small part, we use the Moser iteration. And for the smooth part, we use the spherical harmonic expansion. So I will skip the details. And then by using this estimate of V bar, we can obtain the estimate of gradient U. Okay. All right. Show the optimality of this exponent. Our key observation is that if the domain is symmetric and the boundary data phi is equal to x1, then this v is equal to 1 is a subsolution in this omega tilde intersect with x1 is greater than 0. And then we can use comparison principle to prove the optimality of this bound. Okay, in a second paper, we consider more general case. So instead of delta ij, we consider aij. And also, now this f minus g is not assumed to be radially symmetric. It can be as long as it can be anything as long as f minus g is relatively convex. Okay, so for this A, we assume that it is C gamma and symmetric. And A satisfies this ellipticity condition. So our observation is that indeed, in this case, the Borel rate depends on the geometry. So in fact, it depends on the principal curvature of these inclusions. Okay, so let me define this A C to be this quadratic form, C transpose times this Hessian at 0 times C. And now let's consider this eigenvalue problem on the sphere. So this divergence Sn minus 2 on Sn minus 2 times A C gradient of U is equal to lambda A times A C times U. So this is a weighted eigenvalue problem. And the first eigenvalue is actually 0. So because if you take lambda to be 0, and then you take U to be arbitrary constant, then this is U is an eigenfunction corresponding to the 0 eigenvalue. And we're interested in the first non-zero eigenvalue. Okay, so for that we can define a weighted inner product with weight AC on the sphere, and then this first non-zero eigenvalue can be expressed in terms of this Rayleigh quotient. And then our exponent alpha is actually the positive root of this quadratic polynomial alpha squared plus n minus 1 times alpha minus lambda 1 is equal to 0. And then if you solve this quadratic equation, you get alpha lambda 1 is equal to 1/2 minus n minus 1 plus square root n minus 1 squared plus 4 lambda 1. And in the case when the inclusions are both, then this lambda 1 is exactly equal to n minus 2. So that agrees with the exponent in our previous paper. So this is our result. Again, we assume that U is a weak solution. And then we can, for any alpha less than alpha lambda 1 is in the previous slide, we show that this gradient U is bounded, has this upper bound. Okay. And when alpha is equal to 0, in our paper, we can take alpha to be exactly equal to alpha lambda 1. And in this case, we show that this rate is optimal when dimension is equal to 3. And when dimension is greater than or equal to 4, it is also optimal if the Hessian is close to the identity after certain normalization. And last year, Haigang Li and his student Zhao, they refined our argument, and now they can achieve this alpha to be exactly equal to alpha lambda 1 for general epsilon greater than 0. Okay, so in the remaining time of my talk, let me turn to this conductivity problem with imperfect bounding interfaces. So if the bounding between the inclusion and the background matrix is not non-ideal, then at least one of the transmission condition fails. So let's record the transmission condition. One is the continuity of U, the other is the continuity of the flux, right? So let's consider this typical example. So where you have a core shell structure, so you have this membrane around the core. So this is typical in the biological system. So let's assume that the shell has a thickness T. And this core has a conductivity constant K, and the shell has a conductivity constant Ks. Okay, so let's assume that this T is very small. And also, let's assume that this limit as T goes to 0 of Ks over T exists, and it is positive. So in that case, because T goes to 0, then that means Ks also goes to 0. So that means the membrane is insulated. Okay. then the transmission problem becomes the following. So first of all, the potential can be discontinuous in this case. Second, we have this equation partial u partial nu plus is equal to k times partial u partial nu minus. So that means that the flux is continuous, and they are equal to minus gamma 1 over gamma times u plus minus u minus. So in this case, we say that the inclusion has an imperfect bounding interface of LC type, low conductivity type, and this gamma is called a bounding parameter. Okay, so as I said before, the continuity of potential no longer holds in this case, because u plus can be different from u minus in this case. Okay, so now let's assume that the inclusions are D1, D2. They have a perfect bounding, imperfect bounding interface, and let's assume that in this D1, D2 are perfect conductors. So meaning that K1 is equal to K2 is equal to infinity. In this case, the equation can be written in this form. So Laplace u is equal to 0 in omega tilde as before, and then we have this Robin boundary condition, u plus gamma times partial nu u is equal to capital U j. And also we have this 0 total flux condition as before. And then we have this Dirichlet boundary condition in the outer boundary. And this constant capital U1 and U2 can be determined by using this 0 total flux condition. Okay. So formally, if you take gamma to be 0, then we get the perfect conductivity problem. That means U is equal to some constant. And if you take the limit as gamma goes to infinity, then you divide both sides by gamma, you can see that the normal derivative is equal to 0. So that's the insulated problem. So this problem is something in between this perfect problem and the insulated problem. We can also study this HC problem, high conductivity problem. So if this limit alpha is defined to be the limit as t goes to 0 of ks times t exists and positive, then we say that this is a HC problem, type problem. Because t goes to 0, that means ks goes to infinity. So that means the membrane is insulated, right? So insulating. Okay, so in this case, the potential is continuous, but the flux is discontinuous. So this can be written in this form. So u plus is equal to u minus, and then this difference of these conormal derivatives is equal to this right-hand side. So here, Laplace S and the gradient S are the surface Laplacian and the gradient on the interfacial boundary. And now if we assume that the cores are insulated and alpha is a constant, then this boundary condition can be written in this form. So partial nu of u plus is equal to alpha times Laplace S of u. Okay, so in 2D, this problem is actually can be reduced to this LC type problem by using harmonic conjugate. So this is a special case in 2D. So these two problems are actually equivalent in 2D. So let me mention a very interesting cloaking of invisible phenomenon. So in the LC type problem, if the inclusions are both of radius gamma, then they are actually neutral to the uniform field. In other words, the insertion of the inclusion does not change the uniform field. So this is sometimes called a cloaking of invisible effect. And this has been studied a long time ago by these people. So in the case when the radius is exactly equal to this bounding parameter gamma, then we can easily prove that the linear potential U is equal to xj automatically satisfies this homogeneous Robin boundary condition. So it is actually a solution to this equation phi is equal to xj. So that means if you insert these inclusions into this field, so these inclusions are invisible. So the solutions in the surrounding matrix does not change when you insert these inclusions. In other words, there's no concentration in this case when the radius is equal to gamma. Okay. So there's a recent work due to Fukushima G Kang and Li. So they studied this problem in 2D, where D1, D2 are circular inclusions. And they proved that if U is equal to x2, so x2 is the vertical direction, plus capital O times capital O 1 over x as x goes to infinity. So roughly speaking, they take this dirichlet boundary condition phi to be x2. Okay. Then they show that the U is actually uniformly bounded when epsilon goes to 0. So this is very different from the case when there's no membrane. So actually, with perfect bounding, in other words, if there's no membrane, then this is the typical configuration. Phi is equal to xn. Typically, this du blows up when epsilon goes to 0. Okay. So their result shows that if you add this membrane, even if it is very thin, the solution does not blow up in this case. Okay, so because of this result, they raised the following conjecture. They conjecture that the gradient of the solution is always bounded, independent of epsilon, for arbitrary gamma bigger than 0 and arbitrary boundary data phi. So a heuristic explanation is that biological system cannot endure a large stress. Okay, so in a recent work together with Zhou Yang and Hanyue Zhu, we studied this problem systematically and confirmed that their conjecture is actually true when gamma is small or under certain symmetry condition, but the conjecture is not true in general. Okay, so we have the following three results. So the first result is that in general, we have this upper bound of order 1 over square root of epsilon for the gradient of solution to this LC type problem for general gamma. Moreover, if we assume that the domain is symmetric with respect to the xn direction, and the boundary data is odd with respect to xn direction, then the gradient is always bounded, independent of epsilon. So this result generalized the boundedness result of Fukushima and his co-authors to any dimension, because in their result they assume that dimension is equal to 2 in their result. So we consider any dimensional case, and more general inclusions and more general boundary data phi, as long as it is odd. Okay, so this is the first result. The second result is the uniform boundedness of the gradient without this symmetry condition. So we assume that we prove that if there's a bounding parameter gamma is sufficiently small, then indeed the gradient is uniformly bounded for general domain and general boundary data. So this result confirms the conjecture under the smallness condition of this bounding parameter. So finally, the third result is we proved this dichotomy of field concentration phenomenon. So we proved that when gamma is large, then the conjecture does not hold, and the boundedness of gradient becomes highly unstable, because they prove that if the bounded data is given by xn, then there's no blow up, and we prove that if you slightly tilt this field, then there's a blow up. Okay. So if so that's what I said. If the boundary data phi deviate slightly from xn, then the solution may blow up in that case. So specifically, let's take 2 unit inclusions, unit ball inclusions d1, d2, and omega is equal to b5, and the boundary data is given by x1. So x1 is one of the horizontal direction. We established a dichotomy for the field concentration phenomenon, meaning that the gradient of u remains bounded for any gamma bigger than 0 and less than or equal to 1. Okay. So this gamma is equal to 1 is corresponds to this cloaking of invisible phenomenon, because that's exactly when the radius is equal to gamma. So this is the borderline case when gamma is equal to 1. And then we show that when gamma is bigger than 1, the gradient may blow up. So as I said before, this agrees with the cloaking of invisible phenomenon. Moreover, we established an optimal gradient estimate for the case gamma is greater than 1, and we obtain optimal blow-up rate in this case. So this shows that the solution behaves similar to the insulated conductivity problem in this region. Okay. So that's when gamma is bigger than 1, and you have this insulated membrane, and you have this perfect conductor course. So in that case, the solution actually behaves very similar to this insulated conductivity problem. Okay, so I don't have time to show the details of the proof, so let me mention some ideas of the proof. So first of all, we can use Hopf-Lammer and also maximum principle to show that these two constants, U1 and U2, is between the info for the directly bounded condition and the sup of the directly bounded condition phi. And then we use several different tools in the proof. So first is the boundary C1 beta estimate in the narrow region. So in this case, we have as I said before, we have the Robin boundary condition in the upper and the lower boundary, and this is a very thin domain, and we need to derive certain C1 beta estimate in this case. And then we used an energy iteration argument, and finally we, as we did before, we flattened the boundary and used the dimension reduction technique previously developed for this insulated problem. Okay, so due to the presence of the Robin boundary condition, adapting this method is not pose significant challenges and requires several new ideas. Okay, so finally, let me mention some open questions. So there are actually many interesting problems regarding this imperfect bounding problem. For example, we can consider, because we only consider quite special boundary data, and it is possible to study more general boundary data phi without the ordinates in xj. Okay, so in that case, we expect the du blows up faster due to the non-trivial zeros mode. So this is a work in progress. And as I mentioned before, in 2D, this HC type problem can be transformed into LC type problem by using complex conjugate. So a natural question is, what about higher dimensional case? And finally, we can also consider more general inclusions course where K1, K2 are between 0 and infinity. So this is the non-degenerate case. And for the insulated and the perfect problem, there are also some interesting problems. So first of all, for this insulated problem, we assume the relative convexity of subdomains. So what happens if the inclusions are partially flat? So there's a flat part, and what happens in this case? So we show that in this case that the solution does not blow up. Okay, so this is very different from the relative convex case. And also, in our work, we always assume certain regularity of the inclusions, and in real application, these inclusions can be non-smooth. So interesting problem is to study the inclusions with, for example, conical or wedge boundaries. Okay, that's all. Thank you very much for your attention. So these are the references of my talk today. Thank you.
So, microphones.
Thank you very much. First, Keller, 1963. Second, 1973 for elasticity. It was just conjecture. Conjecture was proved in 2023 first. Do you know Kolpakov's paper, Kolpakov 2006, 2010 books about, because Keller, he considered only regular array. Kolpakov structural optimization, any condition. Moreover, he considered conical wedge and this asymptotic open problem. It is known. It is written in 2006 by Kolpakov.
So he assumed which conductor?
Okay, let us discuss after. Open 10, this. Do you know Kolpakov result? No?
Say again, sorry.
Kolpakov, okay, I'll show you. Second, you said about Amari two-dimensional 2010. It's not the last result. The last result, 2015, Rilko, and you see, you calculate asymptotics, but it's exact solution for two-dimensional problem, exact, and you will see asymptotic.
So I just mentioned some of their results. So there are
so you don't know this paper?
I know this. There are many subsequent work.
Okay. 3, you see, you say about study blow-up condition in multidimensional space. I have the following result. In 2029, I think you don't know this because it's contradictory to your result. I have proved that no blow-up solution for dimension more than 3.
Under which condition? Sorry.
For Laplace equation. For P Laplacian equation, it is, yeah. I have formula I can show you. Well, about, you see, after you consider do inclusion and so on, and look at the asymptotics. Actually, perfectly conductor and insulating in two-dimensional, it's a particular case of Riemann-Hilbert problem. Schwarz operator is. So you may open and take exact formula, exact 1996 for Riemann-Hilbert. Look at the exact formula and you will see this asymptotic. You see? It's in two-dimensional case for this. So if you don't know this, so it's better. Riemann-Hilbert problem. Do you know that this is a particular case of Riemann-Hilbert problem for insulating and perfect? Mm-hmm. Well, about gamma, imperfect contact, you see there is another technique related to coating. Coating with perfect contact. It's in limit, and this result gamma for gamma greater than 0, if you consider as a limit, then its result is evident that no blow up as a limit. Maybe there are some troubles with limit, maybe. So sorry, maybe it's not so. Do you try to consider as coating exact? You see coating is less, and less, and you have imperfect contact. Did you try consider a limit case? So you have a ring and the width of ring going to 0 in a classical problem. Then you have in the limit imperfect contact problem.
So maybe we should discuss this in person because
thank you very much.
So many questions. Yeah.
Okay, thanks for your questions. More questions? Okay.
I keep the number of questions to 2. First is, thank you for your nice talk, number 1. Number 2, there is a series of papers with a totally different approach, which has been authored by Martin Costabel, Bonain Noel, Dambrin, Matteo Dalla Riva, and Paolo Musolino from 2017 to 2021. If you wish, then I will show it to you, that look at moderately closed inclusions. The inclusions get close to each other. I'm not sure that they did gradient estimates as you did, but maybe interesting to see. And then I have a technical question on your talk. Of course, you assume that F is greater than G, but you also add another assumption, that F is greater than G plus a multiple of the modulo of x squared.
Yes, yes.
So.
Yes.
My question is the following. If you believe that by removing this assumption that there is also this extra term, these asymptotics would be completely destroyed or not?
It will be different. So there are some work when people replace this x prime square by x prime to the power m, then the probability is different.
Okay.
Yeah.
Thank you very much.
Thanks.
More questions? Comments? No. Thank you very much for interesting talk.
Okay, thank you.
Yeah. So, we have next talk, Yoshikazu Giga, University of Tokyo, Japan, on a sharp interface limit of the Kobayashi-Warren-Carter system. We are pleased to welcome Professor Yoshikazu Giga from the University of Tokyo, a leading expert in nonlinear partial differential equations. His work on geometric evaluation equations and viscosity solutions has significantly advanced the field. We look forward to his talk. Thank you.
Okay, visible? The slide is visible?
Yeah, okay, everything is okay.
Okay, everything's okay. Okay, thank you very much. Okay. First of all, maybe this should be a bigger screen, maybe. Just a second. Let's see. Okay, this full screen, I think. Okay, first of all, I thank organizers for inviting me to this prestigious conference. It is my great honor to give a plenary talk again. Actually, I gave a talk on the Navier talks in the 5th meeting in Catania 20 years ago. Anyhow, I take this opportunity to thank organizers and technical team so that I can give a talk online. Today, I'm going to talk about simple-looking variational problem and its singular limit. Is it? Do you hear me? Okay.
Yes, we can hear. Could you share your screen?
Oh, I did not share the screen. Just a second.
Yeah.
Can see just the face.
Now we can see. Thank you.
Sorry, we can't hear you.
Oh, sorry.
Okay.
Actually, okay. So this is the contents. Okay, by the way, this is the title of my talk, and my talk is about the Kobayashi-Warren-Carter system. And now this is our contents, and this is Kobayashi-Warren-Carter. They actually, Kobayashi was my former colleague in Hokkaido University when I was a professor of Hokkaido University, and Warren and Carter is
I'm sorry. Could you share the screen?
States.
I think when you go to full screen, the screen disappears.
Ah, I see. Sorry. Just a second. Just a second. This is maybe I should do. No. I should say again. I'm sorry. So if I change full screen, then disappear. So where is it? Yes. Okay. Now it's visible. Okay.
Perfect.
Now it's perfect. Sorry. So this is the first slide. Then I check. Okay. Okay. So. And this is today's talk is based on my joint work, several joint work Okamoto Uesaka, Okamoto Sakakibara Uesaka. And Okamoto is my former student. Uesaka is a former my colleague. Sakakibara is now in Nazarbayev University. And there's many more authors. Kubo is a student of Hokkaido University. Kuroda is a professor of Hokkaido University. And so on. So many papers. So the topic is divided by 3 parts. First of all, what is the singular limit of Kobayashi-Wallen kata energy, and what's the minimizer of the limit of singular limit Kobayashi-Wallen kata energy, and this original model is for the flow. So this is the contents for this is the result for gradient flow. Okay. So let me explain the motivation. Let me explain the original source of the problem. This is the original source of problem is due to Kobayashi and Wallen kata. So, and this is the evolution of multi-grain. And the second one is the potential application. This is the image segmentation or data clustering. And what is the motion of multi-grain? So here's the boundary. It's a 3-phase, and here's the boundary. And interface energy is just sum of these 3 areas, 3 lengths in 2D case. And this is the classical setting. And it's a very classical setting is, okay, this moved by mean curvature or something like that. And intersection in the triple junction, heading angle condition or Young's condition is also imposed. This is often discussed. But if the sigma ij depends on the structure of the phase, it's a little bit different. Assume that each phase has some structural constant like average angle denoted by U1, U2, U3. Assume that sigma ij depends on this angle, difference of angle. What happens? So I should say sigma ij is this coefficient. So this strength depends upon the structural condition in the bulk. And the study by Kobayashi and Wallen kata is a phase field approach, but no motion about this part. And the more recent study, Epstein, Liu, and Mizuno give a different model. And their work is a mean curvature flow plus also bulk, such kind of effect is included. I did not mention about it today. So what is the other potential applications? For example, image segmentation. So draw the counter of project or a particular object in the image. Or this is often done by Mumford-Shah function, or data clustering if there are 3 types of data and then just divide a couple of places, cut of sets. And so what is the Kobayashi-Wallen kata energy? This energy can be written in this way. First of all, this E epsilon SMM, this is a singular modica molecular functional. That means this is the Dirichlet energy plus small coefficient, and f of v is just v minus 1 square, and this is a potential energy, and it's minimized at 1, just 1. And this is the 1 over epsilon. This is single well modica molecular function. Usually this is double well type, but here we need a single well type. And Kobayashi-Wallen kata energy is a weighted total variation. This weight depends upon v. Alpha 0 is typical choice is v square. So this is a v square times mod gradient u. So this is total variation weighted by alpha 0. And v is also such this plus single well modica molecular energy. This is the Kobayashi-Wallen kata energy. And they describe, okay, I explained. The original Kobayashi-Wallen kata fluid, actually, they consider the gradient system of this energy. Yes, they consider the gradient system of energy, L2 gradient system. And it is a weighted one, actually. And tau 0, tau 1 is a positive constant, and this is the gradient flow of Kobayashi-Warren-Kata energy. The epsilon is parameter, small parameter, with respect to weight to the L2 norm, whose weight depends on the solution. So this is the weight. It is well posed. It's well posed. This is still open problem. And what the difficulty is, the second equation includes total variation flow, which is difficult to handle because it degenerates in singular diffusion equation. And if you modify, I want to skip this slide, but if you modify adding some constant and especially putting this nu, positive nu, so that this makes degeneracy is destroyed, then there's a lot of result for well-posedness, initial value problem with Neumann boundary condition. Well-posedness is studied by many authors. However, if you look at the uniqueness of the solution, only one-dimensional case is studied, but degeneracy is excluded. So nu is always positive. There's other degeneracy, so these parameters are often added to avoid degeneracy. But so modified problem, we have a lot of study for the well-posed, but original one still a lot of still open problem. And what is the model? Okay, I show the equation, but I did not mention what it is. Why Kobayashi and Warren-Kata introduced such kind of model. So U is a quantity in each grain, like average angle. And V is the order parameter. V is equal to 1, close to 1. So this order parameter, the order parameter close to 1 is correspond to place where the crystal, it's ordered place. So crystal place. And this is multi-grain. And in between, there's a unordered place. So V is not 1, not close to 1. This is often observed as amorphous. So U is a quantity in each grain, like average angle. So if two angle is very close, then this amorphous is the boundary is in some sense very, very weak. So what is our mathematical problem? Mathematical problem is, okay, let's go back to this Kobayashi-Warren-Kata energy, right? And the basic question, what is the limit of energy as epsilon tends to 0? And the second question, what kind of profile of minimizer for the limit energy? What is a minimizer? And the third question, what is the limit of Kobayashi-Warren-Kata flow itself? Yes, this one, flow itself. And this is we are still in a lot of in progress, but I'm very pleased to give a few results. Okay, so let's start with very simple problem, only one-dimensional case. We consider one-dimensional version of a single well modica molecular energy. This is E epsilon V is dirichlet energy plus potential energy. And if the potential energy is single well, this is single well modica molecular. And if F is a double well, this is we call this double well modica molecular functional. But today we concentrate just single well. So we do not discuss this double well case except next few slides. So what is the limit of the energy? Maybe many of you knows this is a concept due to George, the gamma convergence concept. Does the minimizer converge the minimizer of some limit energy? And what is the limit energy? The gamma limit is defined as follows. E epsilon tends to E in gamma minus limit if the inf inequality holds. And this is, so for any V epsilon tends to V, EV is less than the lim inf of E epsilon V epsilon. So this is the lim inf inequality. This lim super inequality often called recovery, finding existence of recovery sequence. So this says EV is not too small. So for any V, there is a sequence W epsilon combines to V such that EV is actually the limit of E epsilon W epsilon. So this concept, of course, depends on the choice of topology for V epsilon tends to V and W epsilon tends to V, of course. So this is the notion, and U epsilon is minimizer of U epsilon. Then the limit is a minimizer of U, provided that U epsilon tends to U. This is a very good merit of the notion. Of course, one often needs to check the compactness to prove U epsilon to U for some U. So in the case of double wave is if f of V is, for example, V square minus 1 square. This is in this case the answer is well known. The limit, this is L1 limit, is the domain of E is actually a two-value function minus 1 and 1. Yes, I'm talking about this energy minus 1 and 1. And the average equal to 0, assuming that average equal to 0, then limit energy is just the number of jumps of this U. And this C is a computable constant, a positive constant. And this is started by Modica Mortora, so one-dimensional case, and extended by higher dimensional case by Modica himself and Peter Stamberg. And the reason I say the original energy, Modica Mortora, is due to this paper. Here's a typical problem for single well case. Now we consider single well case. So in this case, if V is just V minus 1 square, this one. So in the single well case, typically we ask the following question. If omega, suppose omega is just interval, minus 1, 1, and E epsilon B is positive constant, and V, this is value at 0. So this is the E epsilon with single well potential. Okay. And the question, what is the limit as epsilon to 0? And it turns out L1 convergence is 2 quarts. So what the minimizer? Let's take H1 minimizer. This can be calculated explicitly for Fv minus 1 square. And note that the limit of limit energy is smaller than constant case. And this is also non-negative and less than 1. You see what is the minimizer. You can calculate this explicitly because it's a linear problem even. So the problem is if epsilon is quite large, red line is a minimizer. And if the epsilon is smaller and smaller, you see such kind of very sharp stuff. And of course, if you look everything is L1, these things disappear completely. So we need to introduce different topology. Okay, so what is a suitable topology to catch the above limit? Is it possible to gamma converge under such a limit? So let me mention a few related problems. Ambrosio and Tortorelli functional is, this type of function. This is a fidelity term, but other than fidelity term, the important difference is just the Dirichlet integral instead of total variation energy. And this Ambrosio Tortorelli proved that the gamma limit is actually Mumford-Schacher functional. This is just a Dirichlet energy, and K is a set, and Hn minus 1 is a K n minus 1 has to measure of K, and this is a fidelity term. So, and this Mumford-Schacher is often used for segmentation problem. And the reason Ambrosio Tortorelli introduced such kind of energy is that it's hard to calculate Mann-Hodge functional because K itself is an unknown set. So it's hard to calculate, hard to minimize this one. But instead, this E epsilon EV is just minimizing function, so it is easier. So that's the reason they introduced. And this energy, Ambrosio-Tortorelli energy, has many applications. For example, to study brittle fracture or even Steiner problem. So I did not mention this issue. So what is our problem? What from this point of view? Kobayashi-Wallen-Kata model. This is a kind of Ambrosio-Tortorelli inhomogenization of total variation. Ambrosio-Tortorelli inhomogenization is originally Dirichlet energy, but this is a total variation. This is the main difference. So in the case E epsilon, the limit V epsilon has the same depth, which implies that the set K is a finite set in one-dimensional case. In our case, the depth of limit is not the same. It depends upon the size of jump. The set K can be countable infinite set even in one-dimensional case. So this is quite different compared with Ambrosio-Tortorelli case. So let me explain the relation to Kobayashi-Wallen-Kata energy with this E epsilon sigma. This is E epsilon sigma is where it is. No. Yes, E epsilon. This is we add this type of term, but this term is just not a toy. It's important when you study the Kobayashi-Wallen-Kata energy. Yes, this is Kobayashi-Wallen-Kata. If U is this angle type function is just a Heaviside type, then it's the Kobayashi-Wallen-Kata energy reduced to E epsilon sigma, just we described a few slides before. So what is the gamma limit under this for this energy? So what's a good choice of the topology? So we use this notion of graph convergence. What is this? Let gamma be a set valued function. So this is a set valued function, and B is a subset that consists of bounded upper semi-continuous set valued functions. So more precisely in this word, graph of gamma, closure of graph of gamma is compact in omega bar cross R. So this is a B, script of B. And graph, let me define graph convergence. Graph convergence is a graph convergence. If the Hausdorff distance of two graph is Hausdorff distance of a graph of limit gamma and graph of gamma j tends to 0. In this case, we say this is graph convergence. And for single valued function, we just write in this way just to abuse the notation. So what is the Modica-Mortar function? Modica-Mortar functional is with this term. So this is actually coefficient is delta function. So you get this value. So what is the assumption? This is a FV. This is just a single well, and at the behavior space infinity, this is just does not tend to 0. And the important thing is this VG. VG is GV is just the modulus of integral from 1 to V. 1 is minimizer and square root of F tau. And let me write E0 SMM. This is actually limit energy. This limit energy is if this Xi is a set value function. Xi set value function is L0, which we'll explain later. Then this is just 2 times the Xi minus and Xi plus. Actually, this is some interval valued function at yes. And this is E0B is just sum of this two energy, this energy and B times this energy. Yes, and what is this? Xi. Yeah, A0 is something like this. That this is it's a class it belongs to B, and Xi of X is just a singleton one except countable number of xi, and in this exceptional set, sigma Xi is a interval valued contained in one. Okay, and this is the result of gamma convergence, and V epsilon tends to Xi in the graph sense. Then this is a lower semi-continuous. In particular, Xi is this set A0. So if the right-hand side is finite. Lim-sup inequality is for any Xi, there's a sequence such that this W epsilon combines to Xi in graph sense. And then this is the limit is this can be E0 BSMN. Xi is a limit of this energy at W epsilon. So this is a gamma convergence result. Yes. So now the limit is this type. So G is so this is Xi minus is a jump interval, but Xi is interval valued, and this is a lower bound of interval and upper value of interval. So upper end of interval, lower end of interval, something like that. So you can measure exactly. Okay, what is the graph of Xi belongs to A0? This is a image x1, x2, x3, and this is interval valued by something like that. So we have such kind of limit. And the ideal proof is actually that number 2 is not so difficult. Just construct such kind of things. And in inequality is using Cauchy-Schwarz inequality. You get, if you use G, so here the square is important, we get this one. And this is actually total variation of G of V epsilon. And the key idea is we introduce unfoldings for U epsilon by the arc length parameter of its graph. For a function of one variable U, we define its length. So this is the length of graph at the point x, ux, up to that point x0. Okay. For a function, we define its unfolding U by U of S. This is x of S. X is the inverse function of S of X. So S of X is a length of graph from 0 to X. And we take inverse function. And so this is a graph. For example, if suppose U is a graph of U, then the graph of S is something like that. So its inverse function is like this. So inverse function is very good function. Actually, Lipschitz constant is already less than 1, and so on. And the important thing is the total value of U and total value of U is the same, but Lipschitz constant of U is always big U is always less than or equal to 1. This is a great merit. So suppose U epsilon something like that function, and then maybe this is big U, maybe. V limit U epsilon. U epsilon is unfolding of U epsilon. Then this is original U epsilon, right? And JXI is a set that XS is equal to XI. And this is the closure of such kind of interval, sum of such kind of interval. And this connected component. Okay, anyhow. So if the limit is like this, then V is something like this function if you take limit. So this is so original function is something like this one, but we unfold this function in this way. So this is the key idea. And we also prove the compactness of this, which we don't skip, we like to skip. And then important thing is the minimizer subsequently converges some Xi0 in the graph convergence, and Xi0 minimizes this single well modica mode energy plus extra term. Furthermore, Xi0x is 1 if x is not A, and at the A, Xi0 is P01, where P0 is a minimizer of 2G P plus B P plus square by our theorem. And this turned to be same as we observed earlier, and G must be convex for such kind of assumption, so that GP plus B plus is strictly convex for B positive. In this case, the minimizer is unique. If FV is V minus 1 square, so that G of V is V minus 1 square over 2, then this is computable, explicitly computable. Its minimizer is 1 over B plus 1, and the minimal value is exactly B plus 1. So this is exactly what we found in our example. So we can confirm such kind of explicit calculation. So what is the singular limit of covalent kata? And this is not so difficult once we get the singular limit of modica, single well modica Mortora functional. And this is okay. Important thing is this is a part of singular modica Mortora, but also we have such kind of term. This is already observed in the E0SMMB function, but this is such kind of jump weighted by this one. And this is a remaining total variation outside the jump discontinuity. So the topology is L1 in the graph convergence in L1 in U. The letter is missing, sorry. L1 in U in L1, and the graph convergence in V. For higher dimensional case is more involved, but we have choose a suited topology. So I just mentioned a few words about the covalent kata type total variation. So this is defined in the way we have a limit covalent kata energy with Xi, but take Xi minimizing Xi. So that means minimize Xi minus. Then it turns out this is a jump discontinuity of U, and this is the total variation energy outside jump, and on the jump, this is measured by K of mod U plus minus U minus mod. And this is U plus and U minus is a trace in each direction at the jump discontinuity. And the K rho is defined in this way, 2 0 and Xi square rho. So this is actually minimizing Kobayashi Warren Kata energy. So let me try to minimize in Xi. So this is Xi and this is Xi, so that we minimize this part. Then you get such kind of energy. And if f of rho is rho minus 1 square, then you can explicitly calculate K rho is equal to rho over rho plus 1. Total variation, usual total variation corresponds to case K of rho is just rho. In this case, it's a total variation. But here if you try to minimize Xi, limit Kobayashi kata energy, we get the different total variation stuff. Total variation, Kobayashi kata type total variation. This is defined in this way. And this Kobayashi kata total variation is quite different from usual total variation, since a large jump is welcome for limit Kobayashi kata energy. We consider this Kobayashi kata type total variation with fidelity term as usual. So G is a given function, and lambda is positive. So let's see. So this is of course from the gradient point of view, gradient flow point of view. This is a discrete scheme. Often use discrete scheme to calculate gradient flow. What is the profile of minimizer? And omega is interval. Let u be a minimizer. Then u must be a piecewise constant function. Moreover, so this is more recent work, moreover, the number of jump of u must satisfy some bound. And this C star is depending only on m. So m is just max g minus min g. G is continuous. But this is a little bit surprising, then completely different from total variation energy, total variation, because even if the g, so g is a given function, given image, for example, if even if g has no jump, continuous, or the minimizer must be a piecewise constant. And moreover, the number of jump is dominated by some constant. And this is also can be applied. This problem is also useful to study segmentation and clustering problem. That minimizes such kind of function. So I1, In is some associate partition, and it's associated by U1 UN that minimize this type of energy. So then actually our result says this number of n has a bound, n plus 1 actually, bound. This is quite different from usual total variation case, where in that case, if g is monotone, the minimizer u is just g for this case. Above discrete, there's no bound for n, for k rho and rho. So there's no bound. If you consider this case of just mode, there's no bound. So here is a brief idea of the proof. If k rho is rho 1 rho over rho plus 1, then k is strictly additive in the sense that k rho plus rho 1 is k rho plus k rho 2, but this is even minus some constant rho 1 times rho 2 or rho 1 rho 2 with some Cm. For u, let's see the coincidence set. U is equal to g. For minimizer u must be continuous on C. Also, u must be constant outside C. So we use such kind of property, but this is very common for any k in some sense. Let u be a non-decreasing minimizer of Kobayashi-Wallen-Carter energy, total variation with fidelity. And alpha, beta, gamma is a coincidence set, and it's gamma is ordered in this way, alpha, gamma, beta. And u beta, difference of u beta, u gamma is greater than u gamma minus u alpha. Then assume there's no coincidence set in between gamma beta. Then beta and the difference of beta and alpha should be a little bit should be apart. It's estimated in this way. And here's the profile I mentioned, alpha and beta, gamma, and here there's no coincidence set, so the solution minimizer should jump here just once, I think. So, and so we say this beta minus alpha is greater than such constant. There might be infinity many crazy things happens, but we still have the result. This is a little bit detailed, but if there's no jump, you must have only one jump. We set V, so this is a competitor. Competitor is this function. And then calculate the difference. Total variation, Kobayashi-Wallen-Carter total variation is because of rho 1, rho 2. Rho 1 is a jump here. Rho 2 is jump. And rho 2 is greater than rho 1, or equal to rho 1. And we carefully calculate fidelity term to have such kind of estimate. This is easy. This is a fidelity term is difficult, but explicitly calculate. And if rho 2 is bigger than 1, then this yields such kind of estimate. And it turned out this parenthesis must be non-positive since U is minimizer. So we conclude that beta minus alpha is this inequality. The theorem extends to the case F, general F satisfying this property. So the vanishing at V is equal to 1 is not so not higher order. Okay, so what's the conventional total validation? Conventional total validation, if G is VV has no jumps, if U, the minimizer must have no jump. More precisely, jump discontinuity is included in GJ. Important thing is that in general, U plus minus 1, the middle value, average of U plus minus 1 is between G minus and G plus. So if G minus has no jump, the value is equal to the average of both trace. So this type of result, JU is less than JG, is originally found by Bonforte and Figari long time ago. And there are many extensions, a recent extension by Chambord and Rashica allows arbitrary dimension vector value. So this property, JU is G, is very common for conventional TV type energy. Okay, we have still 10 minutes maybe. Let's talk about the singular limit of Kobayashi-Barrett-Carter gradient flow. Okay, the singular limit problem is as follows. We consider now we put extra parameter A square, V minus Y square. This is still single wave and the weight, and we consider this type of Kobayashi-Barrett type gradient flow. V is a order parameter, while U is something like structural parameter like angle, average angle. And what is the singular limit as epsilon tends to 0? Okay, to avoid all technical difficulty for the U equation, U is the total variation equation, we just consider a very simple case. U is just B times Heaviside function. If V takes its minimum at x is 0, then UB, this above solution, is standing solution, stationary solution of this equation. Time independent, so time independent clear, but it also satisfies this equation with Dirichlet boundary condition, 0. Okay, but we have to be careful because this is a very singular term, and the meaning of solution should be rigorously interpreted in the theory by using the theory of maximum monotone operators. So what is a reasonable scaling? Reasonable scaling is tau 1 is over epsilon with tau 1 positive. This is a reasonable spec. In the Allen-Kahn equation and double well potential, the reasonable scaling is epsilon tau star, not tau 1 over epsilon. So it's quite different. Oh, I'm sorry, this is a plus sign missing. The problem is as follows. Equation is a heat equation with singular coefficient, delta coefficient. Right? And it is expected V tends to 1. How about the behavior of this value at 0? 0 is anyhow value of this singular part. And it turned out limit is not the expected gradient flow, but it turned out it's not a simple gradient flow. it is a kind of fractional time differential gradient from fractional time differential equation. We set tau1 is equal to 1 for simplified to simplified notation, and our equation is of the form. And this is singular modica monotora with p term. It's as follows. So we know that epsilon, it's not part 1, it's a section 1, that ESM tends to ESM as a gamma convergence under gradual under graph convergence. Here B0 BSMM theta is the square root of B squared B theta square plus 2 times Z theta. And Z theta is can be explicitly calculated in this way. So now A is taking square root, we get A here instead of A squared. So limit problem. Since V tends to 1 outside, we are interested in the limit. A naive guess is this one, the gradient flow, but this is unfortunately not correct. So think about well-prepared data in the sense that this is initial data is combines to 1 and with such kind of difference. And this is exponentially becomes 0 as epsilon tends to 0 for large x. So if we take if initial data satisfy this condition, then we get convergence. We have shown solution with equation and Neumann boundary condition with Vt is equal to V0. Assume that V0 epsilon is well prepared. Then the V epsilon combines the set valued function 1 and outside x, and the x is 0 and the closed interval Ct in the household distance sense. And Xi is actually not in the theorem. Xi is actually satisfies such kind of ODE or fractional time ODE. So this is a gradient flow gradient, but also this is a derivative, but we need convolution. MA is a convolution, and this is a F alpha beta defined in this way. So this is a kind of fractional time derivative. And if A is equal to 0, the left-hand side equals fractional time derivative. It's actually Caputo half derivative. And if V0 is not well posed, we have another equation. We don't mention it. Okay, so what is let me ask the simplest question. Consider the boundary solution of the heat equation, this equation, and with Roman type boundary condition. And actually, our problem is in the symmetric case reduced to the Roman boundary condition. And in general, it's a kind of transmission boundary condition, as discussed in the previous talk. So assume that Wx0 is constant, minus constant. Then the boundary value of Ct solves such kind of equation. And in other words, Xa is equal to B Xi. Xi, this is a fractional type derivative. So this is formally reasonable since dx is, of course, half time derivative. So maybe many people knows that the famous paper by Caffarelli and Sylvester, 2007. This paper says fractional alpha minus Laplacian to alpha is obtained as a Dirichlet-Neumann map of the degenerate Laplacian. We are able to assert similar things. We consider such kind of degenerate parabolic equation, and with initial data and with boundary data eta. And initially this is 0. And W of xt tends to infinity, negative infinity. Wx of t is equal to 0 up to negative infinity. And in time 0, this is negative 0. Initial data is equal to 0. Then we obtain this first derivative of W at 0t. It equals to dt gamma eta with some computable constant, positive computable constant. Then you see, yes, we find such gamma for all 0, 1. So this is not so difficult. I show you. We consider such kind of equation. This is not time derivative, it's psi itself, but degeneracy is included. Consider it's minus infinity to 0. And in psi 0 at 0, psi 0 is equal to 1, and psi x tends to 0 at x to minus infinity. Then we take Laplace transform of x, and then we end up with following. Oh, I'm sorry, I think t is missing. Yeah. No. No, we go back to our equation, sorry. Yes, we take Laplace transform, W equation. Then you get such a, in t, we transform in t. So you get such kind of OD. And by scaling, we assume this can be, this ODE is just a scaled version of this ODE. So we can use the psi to write this equation, this solution. And thus, if you differentiate in x, you calculate directly, you get such kind of things, since eta 0 is equal to 0. In other words, W of x, W sub x0t is psi prime 0 times f0 h minus gamma, convoluted by eta differentiated in t. The note that gamma is equal to less than 1, that is alpha is less than 1, guarantees that the integrability of f0 1 minus gamma. We know that psi 0 exists and positive. So this is very simple derivation. Okay, now we are going to discuss summary of our talk. First section, we characterize the singular limit of Kobayashi-Warren-Kata energy. This corresponds to paper by Okamoto and Uesaka, and my joint work with Okamoto Uesaka, and Okamoto Uesaka and Sakakibara for higher dimension. All minimizer must be piecewise constant for the Kobayashi-Warren-Kata type total variation energy with fidelity, even if the original function is continuous. And this is even the number of pieces can be estimated rather explicitly. So, and finally, we show in a very simple setting that for Kobayashi-Warren-Kata gradient flow, the limit is a fractional in time gradient flow. So this has been already published in Proceeding Royal Society of Edinburgh. So as a further problem, okay, I just studied very simple case, and there are a lot of remaining problems. So if we talk about singular limit, a higher dimension, we are able to prove some gamma convergence by introducing, in some sense, sliced graph type convergence, but we don't know the compactness for higher dimension case. So an extension to higher dimension case in the second problem, that means we discuss Kobayashi-Warren-Kata type total variation energy, and we just study one dimensional case. What is a higher dimension analog? This is not known. Even formulation is not so known. Formulation, it's not so clear what's a good formulation for the higher dimensional problem. And of course, in third topic, now in progress, we have to extend more general setting. The setting is too naive. So that's our future directions. So anyhow, many thanks for listening. And I think time is close to the end. Thank you very much for listening. Thank you very much.
So thank you. Questions? Comments? No questions. Thank you very much for a nice talk.
Thank you very much for listening.
So, no coffee break.
Yeah, you have a good coffee break.
All right. Sorry, one more announcement. Please wait.
Just as a reminder, before the next talk at 11:30, we will also have the prize award for Elia Brouet. It will be his talk, but I hope everybody can be here already on time so that we can actually also proceed with the prize award for him without actually delaying the time afterwards.
Okay. Thank you.
Akşam dursunuz söylüyorsun da telefonunuz bilmeydi.
we look after each. Yeah.
Hello, everybody, to the next main talk, which we will start with a particularly, well, happy moment, because already on Monday we said that at the ISAC Congress ISAC is giving 2 prizes, and it's now our time to give the prize of the ISAC Award, which is our traditional prize, which goes back more than 20 years, and which a series of persons got it who actually all showed their capacities to be outstanding young mathematicians. And that's why actually we are more than happy to have this time another young and outstanding mathematician with a bright future to give the prize to. And that person is Elia Brouet from Bocconi University in Italy.
Elia Brouet got his PhD title 5 years ago, in 2020, at the Scuola Normale Superiore di Pisa. Then he went as postdoctoral fellow at the Institute for Advanced Studies in Princeton. After 2 years, he went back to Italy as he was appointed by Bocconi University as professor. Meanwhile, he has been visiting several universities, among which ETH Zurich, EPFL Lausanne, Oxford University, Shanghai Tech University, and let me say that his research interests range from geometric analysis and PDE to works related to Ricci curvature, metric geometry, incompressible fluid mechanics. His scientific production is impressive. He has already about 30 papers, all of them published in first-rate journals. Let me mention 2 papers published in Annals of Mathematics, one already accepted there. Then he published on Invenciones, Journal of European Mathematical Society, Krelle's Journal, Geometric and Functional Analysis, Journal of Functional Analysis, Communication in Mathematical Physics, and so on and so forth. So for his achievements in analysis, the jury members had no doubts to award him the ISAC Prize 2025. Congratulations. So to give a flavor of his work today, he will present some results revolving around an open problem about the uniqueness for solutions of the 2-dimensional incompressible Euler equations for flows with vorticity in LP spaces. The title of the presentation is To the Euler Flows, Non-Uniqueness, Instability, Flexibility.
Okay, so first of all, thank you, Ilaria, very much for this very beautiful presentation. I'm deeply honored to receive this Isaac Award, 2025 Isaac Award, and I'm very grateful to the committee, the scientific committee, and all the organizers of this very beautiful Congress. Yeah, let's turn to mathematics, which is the main reason why we are all here today. Today I want to present a bit of my work about Euler flows. So this is based on a series of papers in collaboration with Maria Colombo from EPFL and Anuj Kumar from Berkeley. And the main focus is the study of weak solutions to the Euler equations. And the main motivations behind these constructions come from the theory of turbulence. I'll briefly mention those motivations. This is not going to be a talk on turbulence. And the second main motivation is related to a long-standing open question which arose after a classical famous theorem by Udovich. I'll provide a precise statement of that in a second. Okay, so let me thank you. Let me start. Okay, that's the model I want to consider. This is just incompressible Euler. I think we have seen already in this Congress at least 3 times this system of equations. But I think it's worth displaying them again, so it also allows me to introduce my notation. So U here denotes the velocity field. The system of equation, they describe the evolution, the implicit evolution of a fluid flow under the incompressibility condition. And U is the velocity of the fluid flow. My domain here is the Euclidean space of dimension D, and D will be mainly equal to 2 and 3 in this talk. I'll sometimes assume periodic boundary conditions, so making the domain the torus, the dimension of torus. So P here denotes the internal pressure, and F is an external body force accelerating and decelerating fluid particles. You can think of it as gravity, for instance. Now, as I said, the main focus is on weak solutions. And to motivate their study, I want to very quickly present a few important features of Euler equations, Navier-Stokes equations, in relation with turbulence. Now, the first observation is that the Euler system is a conservative system. So there's no diffusion in there, and it is supposed to model the evolution of a fluid flow in a regime where viscosity is very, very small. And this actually can be rigorously checked. Let's assume for simplicity that there's no body force, and let's make an important assumption. Let's assume that the velocity and the pressure are smooth, and let's assume some good decay at infinity. Then an easy calculation based on integration by parts shows that, in fact, the kinetic energy is conserved, doesn't change in time. But actually, this is not what we see, or what people see in experiments and simulations. In certain regimes, the energy conservations, it simply doesn't hold. Back in 1949, Onsager made a very precise mathematical conjecture on this possibility of having anomalous dissipation in relation with the regularity of the solution to the Euler equation. And the conjecture, which nowadays is a theorem, I'll elaborate more on this later on in the talk. The conjecture is that below a certain Holder regularity threshold, one might be able to find solutions of the weak solutions of the Euler equation such that such that the energy conservation identity simply doesn't hold. Energy dissipates. And this point is very, very central also in the famous K41 theory of Kolmogorov. So I don't want to enter into the details of anomalous dissipation, but I just want to convey a clear message. In order to model certain turbulent solutions, it is necessary to rely on weak solutions. Solutions belong to certain weak regularity class. Because as soon as you assume enough regularity, then you cannot simply see certain phenomena such as anomalous dissipation. All right, I hope I convince you that weak solutions are kind of worth studying, and let's move on. Now, I want to consider the two-dimensional case. And here, there's an interesting variable to consider, vorticity, which is nothing but the curl of the velocity field in two dimensions is going to be a scalar. And we can rewrite the Euler equations in terms of the vorticity. And it turns out that they have a very nice structure. They have a structure of a transport equation with a forcing term, if you want. And the velocity field U can be written in terms of the vorticity by inverting the curl relation. And what we get is this operator, is the Biot-Savart law. Okay? Now, let's make a few easy observations. So first of all, if we assume that the external body force is 0, we just get a transport type equation. And again, under suitable regularity assumptions, one can check, is just chain rule, that if we compose omega with any scalar function beta from R to R, a smooth scalar function beta from R to R, then beta omega is going to solve the very same equation. This is somehow called renormalization property of transport type problems. But then, we can infer that we have many, many conserved quantities in this two-dimensional setting. So the integral of beta vorticity for every beta is going to be conserved. It simply follows by integrating the transport equation in the 1, 2, 3, 4th line. In particular, the expectation is that if the initial vorticity belongs to LP, then the LP norm of the vorticity is going to be constant in time, at least in well-posedness regimes, when we have good and regular solutions. And this is somehow suggesting a nice class of weak solutions to look at. Now, let's complement the problem with some initial conditions. So let's pick some initial vorticity omega 0. And given the invariance I presented in the previous slide, the expectation is that an initial vorticity in LP is going to give rise to a solution whose vorticity belongs to LP uniformly with respect to time. At least this is the case if you assume smoothness a priori. But then, let's see what happens at the level of the velocity field. Some nice linear operator, differential operator of order 0, which is Calderon-Zygmunt, applied to the vorticity. In particular, when the vorticity is LP, with P between 1 and infinity, the differential of the vector field is in LP as well. So the vector field is Sobolev regular. When P is equal to infinity, we cannot quite conclude that the differential is bounded, or the differential of the vector field is bounded, but it is almost bounded. So it looks like the vector field is almost Lipschitz. It's supposed to be almost Lipschitz as soon as the vorticity is bounded. Now, given that in the linear theory, if you want to solve a transport problem, and you have given some velocity field, which is Lipschitz regular, then it's standard. It's Cauchy-Lipschitz theory. And we can show that the problem is well posed, the solution to the transport equation is expressed in terms of the Lagrangian flow of the vector field, and so on and so forth. But actually, again, in the linear setting, this is the case even when when the velocity field is not Lipschitz, but Sobolev regular. This is a much more difficult result, which dates back to Di-Perna-Lyons in 1989, and it has been improved and generalized to the BV setting by Ambrosi in 2004. I think I'll mention some specific statement later on about this. But essentially it says that if you have a Sobolev vector field, maybe you don't have a well-defined point-wise flow, but still you have access to some weak notion of flow, and you can use it to solve, to show well-posedness for the transport problem. But those are linear statements. Of course, they don't imply anything about well-posedness of the nonlinear problem, but still, this is kind of suggesting that in this regime, when the vorticity is LP integrable, some sort of rigidity should be there. Now, this is the classical and famous result by Udovic I was mentioning at the beginning, and it says that when p is equal to infinity, actually the nonlinear problem, the Euler equations are well posed. Here, for convenience, I'm considering periodic boundary conditions, but it's not so important. There's an analogous statement also in the Euclidean space of dimension 2. And so the statement is simply that pick any bounded vorticity, then there exists a well-defined flow. We can solve the Euler equation. There exists a unique solution, and this unique solution has a vorticity which is uniformly bounded. Okay. Now, one can generalize a bit this result. There are contributions by Udovic, Wyschik, by allowing for some mild growth of the vorticity. And on the side of existence, it is possible to show that there exists a solution to the two-dimensional Euler equation with vorticity in LP uniformly with respect to time for any initial vorticity in LP. And here P is any exponent between 1 and infinity. So P equal infinity, existence and uniqueness, there's a well-defined Euler flow. P between 1 and infinity, existence has been proven, and the question is about uniqueness. So is it true that given any bounded vorticity, any LP vorticity, there exists a unique solution in this class, in the class of LP vorticity, LP in space, L infinity in time? And this question, when the external body force is arbitrary or equal to 0, is still open. But recent developments suggest that the answer is more likely no than yes. And today I want to show two pretty strong evidence of no uniqueness for this problem. One is based on instability and is a result by Wyschik. And I also talk a bit about some consequences of this result. And the second evidence is more related to Onsager conjecture turbulence, and it has to do with flexibility and the convex integration approach, which has been a very important technique developed in the last 15 years. All right, so first evidence of no uniqueness. This is Wyschik theorem from 2018. In 2 papers, more than 200 pages, Wyschik managed to show the following. So let's pick any exponent, p, bigger than 2, but smaller than infinity. Then we can design a very special external body force, F, which is L1, L2, and the curl of this external body force, actually the whole gradient of this external body force, is L1 in time, L2, LP in space. So actually, this force is much better than this, is completely smooth for T positive, and for T equals 0, it has only one singularity at the origin of the Euclidean space of dimension 2. But globally, those are the integrability properties it satisfies. Now, given this force, we can solve the two-dimensional Euler equations, the Cauchy problem associated to the two-dimensional Euler equations with initial vorticity simply 0. And we get two distinct solutions, actually infinitely many, but at least the two distinct solutions. And they are solutions in the energy class, but more importantly, the two vorticities belong to LP, L1 intersection LP, in space uniformly with respect to time. So this is telling us that if we allow for some singular, very special external body force, then we immediately get no uniqueness. Okay? Let me maybe say something about the features of this example. So the first keyword here is symmetry breaking. Indeed, here what happens is the following. We have an external body force which is radial. It depends on time, but is radial. Does not depend on the angular variable of R2. So in particular, the initial condition, of course, is radial. I mean, it's 0. So given the symmetries of the Euler equations, one expects that solutions to such a problem to be linear. And indeed, the first solution, omega 1, is radial, while the second solution is not. The second solution depends in a non-trivial way on the angular variable. And the responsible for this symmetry breaking leading to no uniqueness, again, is the external body force. So the very strong singularity of the origin of the external body force produces instability on a certain subspace where functions depends in a non-trivial way on the angular variable, and out of this instability we get this second solution coming out. It's essentially a trajectory on the unstable manifold in a certain coordinate system. And this result has been simplified and improved by many people. Actually, the first simplification and improvement goes back to 2021 when I was a postdoc at the IIS, and with a group, it was during COVID, with a group of 7 people, we studied Wyshik paper and we try to kind of make it more accessible. And this version of the theorem with 0 initial condition is presented in these lecture notes from 2021. The original result by Wyshik is with some singular initial condition too. And another interesting point is that this construction has some connections, at least moral connections, with another no uniqueness scenario for the two-dimensional Euler equation, which has been presented by Bressan and Shen in 2021. In their case, there's no external body force, so the instability is more related to the singular initial condition. But in their case, there's no rigorous proof yet. So there are compelling numerical simulation about this no uniqueness scenario, but so far there are no rigorous proof of the existence of this form of instability and no uniqueness. Now let me maybe say just something more about the Wyshik construction. So the idea is to exploit instability in self-similar variables. The main achievement, I mean, one of the main achievements in Wyshik paper is the construction of a special vortex, capital gamma 1, which is literally a vortex in R2 with a property that is unstable for the Euler equation. So if you linearize the Euler equation around this vortex, you can find unstable modes. You can find eigenvalues with positive real part. Now, a vortex is a steady state for the Euler equation, but in order to use instability to force no uniqueness, we have to change the coordinate system, look at the similar variables, and the vortex is no longer a steady state. That's why we generate a singular external body force. But then, if you still think of the vortex in the similar variable as a steady state with a body force, you can try to construct the unstable trajectory coming out of the unstable mode, and this is going to give you exactly the second solution to the problem. That's essentially the idea of the construction. Here is the picture of the easiest possible example of Hamiltonian system with a hyperbolic, with a steady state and unstable modes. All right. Just one slide on developments of this technique introduced by Wyszczyk. In a subsequent paper, in collaboration with Dallas Albritton and Maria Colombo, we tried to apply this general framework to establish no uniqueness to attack another pretty famous problem, which is the question of uniqueness of weak solutions to the Navier-Stokes equations in 3 dimensions. So this is nothing but the 3-dimensional Navier-Stokes equation, the same system appearing in the formulation of the Millennium problem. And back in 1934, Leray proved that in the energy class, so in the class of solutions that are L2 in space uniformly in time and H1 in space L2 in time, one can construct global solutions. And then a natural question, which appears already in the 1951 paper by Hopf and has been considered also by Ladinzenskaya in 1969, is about uniqueness of these weak solutions. And again, if we assume F equal to 0, or we want to establish uniqueness for generic body forces, this is still an open problem. But what we managed to show in 2023 is that there exists a very special body force, exactly as in Wyszczyk theorem, creating no uniqueness. So we solve with this special body force, which again is self-similar, is smooth away from one point, essentially. And it generates 2 distinct solutions, infinitely many actually, starting from the 0 initial condition. And again, here there's some instability going on, building this family of non-unique solutions, and this instability is strictly connected to the unstable vortex by Wyszczyk. It's some sort of 3-dimensional lifting of vortex instability. All right, so let's go back to the original problem, so 2-dimensional Euler. This second part of the talk will be about the second strong evidence of no uniqueness, the one based on flexibility and convex integration. I want to just quickly recall what convex integration is to begin with. So construction of wild solutions to the Euler equation is an old business. And the first result is due to Scheffer and Schnirelmann, 1993-1997, where they managed to construct weak solutions to the Euler equation that are compactly supported in space and time. So in particular, they don't conserve the kinetic energy. So if you remember, in my second slide, I talked about energy conservation and the fact that the smooth solutions do conserve the energy. Those solutions that are just L2, so in particular they are weak solutions, they don't conserve energy as they are compactly supported in space and time. But then, later on, starting from 2009, Delelis and Zvekilihidi found a general framework to construct such a pathological examples to the Euler equations. And the main achievement of this technique has been the solution. I mean, actually, there are many interesting achievements, but maybe the most famous is the solution of the Onsager conjecture that I displayed at the beginning of this talk. The first part, so the rigidity part of Onsager conjecture, was established by Konstantin Iti back in 1994, and this has nothing to do with convex integration, is the flexibility part, so the construction of dissipative solutions with the Holder regularity C alpha with alpha smaller than 1/3. This has been achieved using convex integration, starting from the 2013 paper of Camillo and Laszlo. There has been a series of improvement on the regularity of these wild solutions, culminating in the final paper in 2018 by Iset, where the conjecture was solved. And then this approach has been reinvented and generalized in many different ways. And one of the most important applications after Onsager conjecture has been the construction of the first no uniqueness and flexibility of very weak solutions to the Navier-Stokes equation. And this has been achieved by Buckmaster and Vicol in 2018 with this important idea of adding intermittency in the convex integration scheme. Then it has been applied to active scalars, even passive scalars, and if time allows, I'll say something about that at the very end of this talk. All right, that's an available and very powerful technique. Let's try to attack the problem of uniqueness of weak solutions with vorticity in LP spaces using convex integration. And this has been our first attempt with Maria back in 2021. And actually what we proved wasn't so satisfactory at the time. We could construct convex integration solutions, very flexible solutions, so they are non-trivial and they have compact support in time, exactly as in Scheffer and Schneiderman paper. In our case, the velocity field belongs to the energy class, that's good, but the vorticity is not so good. The best we can say about the vorticity of our solution is that it belongs to a weak L1 space, to the Lorentz space L1 infinity. It doesn't belong to L1. But actually, we can also show that the velocity fields belongs to fractional Sobolev spaces, WSP for every S smaller than 1, and P in a certain range of parameters. So this does not quite solve the problem, as the vorticity enjoys some regularity, but is not even L1 regular. Then Bach and Modena in 2023 improved upon our result, and they showed that there are dissipative solutions, so the kinetic energy decreases in their construction, with vorticity in the Hardy space HS. But again, they have the constraint S smaller than 1. So again, those vorticities are not integrable. So it seems that there's something preventing convex integration to construct flexible solutions with integrable vorticity. And actually, that something is a deep structural point of the convex integration construction. And to explain this, let me very quickly provide some high-level explanation on how convex integration works. So the idea is to relax the problem. So we study subsolutions, meaning that, well, we have something, and this something doesn't solve the equation, so we have a remainder. And we call the remainder R naught. We write it as the divergence of some tensor, and this tensor is the so-called Euler-Reynolds tensor. Reynolds tensor, actually. Then the plan is to start an iteration, and at each stage of the iteration, we add high-frequency terms to the solution at the previous step with the goal of decreasing the size of the error, and eventually, in the limit, get 0 as a left-hand side of the equation. And I like to think of this construction to some sort of inverse filtering procedure. So imagine that you have given some turbulent solution to the Euler equation, and in order to study it, one might consider to filter and cut away all the high frequencies. I mean, if the solution is turbulent, there are many, many small scales, respect the structure of the Euler system. And indeed, what you get out of this filtering procedure is a solution to the Euler-Reynolds system, where the error R0 has to do with the commutator between the nonlinearity of the equation and the filtering procedure. Now, the Gaulish convex integration is exactly the opposite. You give me something which looks like a filtered turbulent solution, and I'll show you how to get back to the original turbulent solution by adding back all the high frequencies step by step that have been cut away. And indeed, this is the more or less the general idea of how you perturb the solution at the qth step to get the solution at the qth plus 1. You simply add linearly a term, and this term has a precise structure. So first of all, the main part of this term, the typical frequency of the solution at the qth step of the iteration, and it increases very quickly. It's hypergeometric. So lambda q plus 1 is way bigger than lambda q. So this new term has a main part, w lambda q plus 1, oscillating at this new frequency. And in front of this, there's a slow coefficient. A slow coefficient is something depending on the error at the previous stage, so it oscillates at frequency lambda q, making it almost constant from the point of view of the building block. And the role of this slow coefficient will be clear just in a second. So essentially, I'm re-adding back high frequencies at each step by, designing in a correct way the slow coefficient. So actually, there are, in order to close the scheme, W has to satisfy certain constraints. So for instance, it has to be a steady-state solution to the Euler equation, or it has to be close to a steady states of the Euler equation. So there are important constraints on these building blocks. But now, what's the point of this perturbation? Well, we have UQ plus 1, and now we can plug it into the equation. And we are going to get many terms. We have many linear interactions between UQ and the perturbation. Those are in general small. We don't care about linear interaction, at least in certain cases. The important term is the quadratic interaction, is when the new oscillating term interact with itself. And that's given the nonlinear structure of the equation, the quadratic interaction is given exactly by the square of the slow coefficient times WQ plus 1 tensor WQ plus 1. And now the idea is that, well, we have an interaction between high frequency waves, and out of this interaction, we would like to extract a low frequency term. And so we use this low frequency term to cancel the error we made at the previous step. Now, to extract a low-frequency term from this interaction, we just need the first Fourier mode of the interaction to be of size 1. And this amounts to the constraint that the integral of omega tensor omega is more or less 1. So if you want, W has to be normalized to have norm 1 in L2. That's what you need. And then you want to design the slow coefficient A in such a way that the square of this low coefficient is more or less the error at the previous stage. And so you can use that to eliminate the error at the previous stage. Then you have to take care of all the other terms and so on, but this is the key point. So we want to get advantage of the quadratic interaction to reconstruct the error at the previous step. And to do so, we have a constraint that we cannot drop. The building block is normalized in L2, to have norm equal to 1. But that's why it's impossible to get a vorticity in L1. It's just Sobolev inequality. So the vorticity is one derivative of the velocity field. If you check the differential of UQ plus 1, the most important term is the differential of the high frequency term, W lambda Q plus 1. And this differential is going to be of size lambda Q plus 1 times the L2 norm of the differential of the building block. And lambda Q plus 1 is big. It's like blowing up at a hypergeometric rate. But on the other hand, the L1 norm of the differential of V by Sobolev inequality is bigger than the L2 norm. We are in dimension 2 of W. This has to be normalized to be 1. So all in all, the term we had has differential in L1 bigger than lambda Q plus 1, something which goes to infinity pretty quickly. That's why it seems impossible to get out of this technique something with a solution with integrable vorticity. And that's why all the results based on convex integration were in all cases, the vorticity was Sobolev fractional, Sobolev regular in Hardy spaces, but never in L1. But then, the last part of the story, we managed to reinvent the quadratic cancellation of the error in convex integration. And this allows us to go slightly beyond L1 integrability of the vorticity. The threshold we got is a bit funny. I don't think it's sharp, but it's some number bigger than 1, 1 plus 1 over 7,000. And given such a P, we have two statements. One is flexibility and one is non-uniqueness. Flexibility essentially says that if you give me two velocity fields, divergence-free reasonable velocity fields, up to an error epsilon, I can connect them with a solution of the two-dimensional Euler equation with vorticity in LP. So essentially, the problem is super flexible in this regime. When the vorticity is LP with P slightly bigger than 1, the problem is very, very flexible. You can literally connect any two velocity fields up to a small error with a solution to the Euler equation. And the second statement is about, of course, in particular, this implies that energy is never conserved. Entropy or whatever function of the vorticity, the integral of every function of the vorticity is not conserved. And the non-uniqueness part simply says that we can find many initial conditions with giving rise to infinitely many solutions to the Euler equation with zero body force, and again with vorticity in LP. So in particular, this solves the uniqueness question by the long-standing uniqueness question, at least for a very limited range of exponents, P very close to 1. Now, a few remarks on the structure of the solutions. So let me anticipate, they are not very physical. Now you will see why. Of course, they don't conserve the kinetic energy. They don't conserve the LP norm of the vorticity. And actually, there's a result, a positive result, by Cheskidov, Konstantin, Frilander, Zvitkoi, saying that if you pick a solution to the Euler equation with vorticity in LP, exactly as in our example, but as soon as P is bigger than 3 over 2, then the energy is conserved. Uses very well solutions. And this poses a natural question. So 3 over 2 is the threshold to get, in this Sobolev scaling, 3 over 2 is the threshold to get conservation. We have the first example of non-conservation when P is close to 1. What about the interval 1, 3/2? Is it true that one can construct dissipative solutions for every P smaller than 3 over 2? And this is somehow connected to the Onsager conjecture, and it's, as far as I know, it's open. The only result in this direction is the theorem I showed you before. Now, another important exponent in this business is 4 over 3. as in order to make sense of the distributional formulation in vorticity formulation of the Euler equation, formulation in vorticity doesn't make sense. When I say that we have a solution to the Euler equation, I mean a solution to the Euler equation in velocity formulation with a bound on the vorticity. What we can check is some weaker form, like the symmetrized weak vorticity formulation is okay in our setting, but not the distributional formulation in vorticity formulation. And finally, that's why I anticipated that our solutions are not very physical. Vorticity, they conserve the energy. So in particular, our solutions have integrable vorticity. They don't conserve the energy, so there's no way one can get those solutions starting from Navier-Stokes or reasonable regular. I mean, the main new ideas behind this new convex integration construction. But some of them are a bit technical, as the convex integration approach in general is a bit technical, and I mean, it's pretty advanced right now. I think I'll just focus on the first point. So I want to try to explain the main new idea, which is this spatial inhomogeneity we tried to add in the construction, or Ambrosio framework. So let's consider for a second this toy model. It's just anticipated at the beginning of this talk in the Sobolev regular setting, and I'll also assume that the velocity field is divergence free. So I want to consider again the incompressible framework. So when the velocity is Sobolev, there are results about well-posedness of generalized notion of flows and transport equation. And typically the vorticity is taken in LP spaces, LR spaces. And here is the very first result in this business, a theorem by Diperne and Lyons back in 1989. And it says that the PD is well-posed. So the Cauchy problem is well posed. You can solve it given any initial condition. You get only exactly one solution. If you have this relation between the Sobolev exponent of the velocity field and the LP exponent of the passive scalar of rho. Then, by convex integration, so this is a convex integration result applied in this linear setting, Modena, Svekeli-Hivi, and Modena Sattig managed to show that the problem is ill-posed as soon as you are in this range, 1 over P plus 1 over R, bigger than 1 plus 1 over D. And notice that, I mean, for this talk, it's not super important to focus on the nature of this ill-posedness result, but I want to just look at the numerology. So this is the range by Diperne-Lyon, and this is the ill-posedness range. There's a gap in between. And we tried for a while to close this gap. And in 2020, in collaboration with Camillo and Maria, we realized that actually the well-posedness result by Diperne-Lyons can be improved a bit, at least if you assume something on the sign of the solution, but this is technical. Let's forget about this. So the Diperne-Lyon result can be improved a bit up to this range. 1 over P plus 1 over R smaller than 1 plus something else. 1 over D plus R. And again, I just want to focus on the numerology. This is a third range. It's more general than Diperne-Lyon, but it doesn't match with the ill-posedness range obtained by convex integration. And so again, now the gap to close is between this range and the convex integration range. And only very recently, last year, we realized that the new range, the one we got in the paper with Camille and Maria, is the sharp one. And the problem is that convex integration cannot beyond, for structural reasons, cannot go beyond that range, while another construction, completely different, is a linear construction, is able to overcome this range and get up to the sharp. And this new construction is what inspired us to modify convex integration in the Euler framework, because we can clearly see what's the weak point of convex integration and why it kind of stops at a certain range, which is not the sharp one. And the key word here is homogeneity. Convex integration, perturbations in convex integration are too homogeneous, and this strong homogeneity is gonna create structural constraints. And indeed, I want to conclude with one picture, which depicts a bit the linear evolution in this toy, the linear evolution in the counterexample in this toy problem. So what we managed to do is to find a solution to a transport equation within that range, connecting these two configurations. One is just the uniform density on the torus, literally like density, the constant density 1, while the second solution is a density which is concentrated in these 4 boxes and 0 outside. And of course, if you can find a solution to a transport equation mapping the constant density into the non-constant density, you get no uniqueness, as the constant density is always a steady state. And here is a depiction of our construction. So let's go in the opposite direction. Let's start from the 4 boxes and try to get to the uniform density. Now, the plan is to break these cubes, these boxes, in different steps. And what we do at the first step, we just break we pick one of the 4, we break it in 4, and then we make a rigid motion to simply translate the 4 smaller cubes back. Now, we pick one of the 4 small cubes, and we break it exactly as we did at the previous step, and we move it back. Then we again pick one, and so on. And once the bottom left part is completely done, once we get to the uniform density there, we restart the process with the other cubes, and so on. Now, this seems a bit inconvenient and strange. And one could argue that it's much better to kind of break all cubes at each step. So if we pick the first 4, we can simply break all of them. So we get 4, 4, 4, 16. We break all of them, and so on. That was the first attempt. If you do that, you get convex integration range. You get no uniqueness, but you get exactly in the range of convex integration. To gain the tiny bit of integrability you need to get in the sharp range, it's much more convenient to break only one cube at a time. You want to intervene on the smallest possible region of space at the time. And that's the insight we tried to bring into the convex integration construction. And I mean, the convex integration is more complicated, it's non-linear, and so on and so forth, but that's the main insight. And yeah, it partially worked. And yeah, I think that's all I wanted to say, and thank you very much for your attention.
Thank you very much for your very crystal clear and inspiring lecture. So for the audience, are there any questions or comments?
Yeah, thank you very much indeed for the wonderful lecture. So I wonder, so in the case of convex integration, I'm sure that it's not constructive. You don't have a explicit form of initial condition. But in the other case with the singular force, is it constructive? Do you have a force exactly?
So you mean in Vichyk theorem?
Yeah.
So in that case, it's kind of explicit in the following sense. Let me just go back. Okay. The, say, most explicit object is this profile capital gamma 1, omega 1. This is a vortex. The profile of this vortex is not super explicit, but I mean, we can describe it. It has inflection points. It's something that we can describe. And it's globally, it's just a vortex. It decays as a power law decay, inflection points. Now, given this vortex, the first solution is literally that one. So we use self-similar coordinates. And then you plug this into the equation, and you get an essentially explicit formula for the external body force, which involves derivatives of this object. Then the second solution is essentially constructed, it's a trajectory on the unstable manifold. So it's a perturbative argument. There are, kind of explicit elements, but it's...
And then I guess if you take Navier-Stokes with this forcing, it will be well posed, right?
That's a very good question. There's a paper I think is about to be posted on Archive by my colleagues Maria and Dallas. They studied the problem this external body force plus nu Laplacian, or 1 over Reynolds Laplacian. Now the body force is it's good enough to make the problem well posed. So the problem is well posed. Now the question is what happens when you consider the vanishing viscosity limit. Right. And what happens is that if you don't add any initial condition, then you just converge to the first solution, the radial one. But if you add some initial noise, then in the limit, or if you add some initial condition, then what happens in the limit depends on the size of the initial condition. There's an explicit threshold depending on the viscosity, and if the size of the initial condition is below this threshold, there's literally some power of nu, the viscosity. If the size is below this threshold, then you will always converge to the radial solution, to the good one. If it is above the threshold, you can design the initial condition. I guess this is a very unstable procedure, but you can design it in order to fall in one of the unstable non-radial solutions of the Euler equation. This is the picture.
Thank you very much.
You're welcome.
Are there other questions or comments? Please stand up if you have any remark or questions. It seems that it is not the case, so we thank the speaker again.
Thank you.
So the sessions are resuming in the afternoon, according to the program.
We have the same schedule as we had on Tuesday. So session talks start